There were a lot of big ideas in the last talk. This is going to be a sort of a technical, how do things work, how do they plug together? I think in the abstract I said about building a mental model so that we understand these systems, because I have to work with them every day, and I always have to think, when something's gone wrong, I always have to think, wait, how does the sprocket plug into the doodah, and how does it all work? So my general agenda today, this looks a little bit boring, but hopefully there's more pictures coming later. I'm going to go through sort of cloud VPC, like what that looks like compared to what you might have as a traditional network, logically what it gives you, what promises, what contracts it gives you, and how it's built. And then I'm going to do the same for the cluster, the network within a Kubernetes cluster, and then this service construct within Kubernetes, and then service meshes as well. So this, I call it taming the turtles, because there's all these layers of abstraction, all these layers of virtual network that all plug on top of each other. And a question I get asked quite a lot is, do they not interfere with each other? Where am I vendor X or product Y says it uses BPF for this? Where does that live? How does it all get contained? So I think I've rearranged all the slides last night to I think a slightly better way of explaining it, but we'll go through it and hopefully sort of build up that picture. Just so this is a really good conference and a super sophisticated audience. Like who is like a Kubernetes user? Okay, cool. And who would say they're a decent admin who could install one from scratch if they were pushed? Okay, you know quite a lot of this then. And who's got hands-on with a service mesh? Okay, cool. Right, well let's begin then. I can go faster or slower, and we can take some questions at the end. So just to get us all on the same page, I'm sure everybody will, you put up a diagram like this, it's wrong to everyone, right? But it's hopefully the least wrong to the most people. If I have a sort of traditional on-premise network, I just want to ground it in this model for folks who've dealt with this kind of thing. If you haven't done any traditional networking, if you're in your 20s or something, you're very lucky. We won't need to know this, but if we think about how a traditional network, might work with a connection from the internet and a firewall, and then a DMZ, and then another firewall, and I hang some subnets off the firewall where I can afford enough firewall ports, and then when I run out of expensive firewall ports, I buy a core router and I hang some more subnets off that. We might have a traditional network that looks a little bit like this, and the point is, I guess, that we're sort of segmenting by security domain. We've got certain centralized points of policy enforcement, and then I've got these subnet. I say apps. This is all of your line of business apps. This is all of your appliances. This is like everything else. I'm not showing a particularly sophisticated thing here. I've got all these places where my applications live, and they all want to talk to each other. And there's some rules that say when they can and when they can't. So a VPC, like a cloud network that I get from, I'm going to mostly focus on AWS because it is the most widely used. It's also the most traditional in the sense of in the network abstraction that it gives you. They really optimize for lift and shift. They're trying to give you a network that looks like an on-premise network, not like Google's tried to give you something that might be ergonomic for more modern workloads, but it's got some surprises if you come from the old world. Other clouds are available. So we've got an AWS account. This is our universe. I won't draw a box because we're going to have so many boxes. But in our AWS account, we have a VPC. This is actually in a given region because VPCs are a region scope. So what is that VPC? Well, it's a network and it can span multiple AZs, right? As they say in AWS, they stay within a particular region, but it can span multiple AZs, multiple data centers if you want to think about it like that. For simplicity, I've just drawn 2, but obviously we love Raft. Most regions have 3 these days. Well, what do I do with that? So before I use my VPC, I need to divide it up into subnets. So the VPC has a CIDR, which is really only an accounting thing, the address range, the sort of /16 or whatever on the VPC. It doesn't really mean anything other than I can only take subnets ranges out of that larger range. So these subnets have to live in an AZ, and I guess everybody's probably going to recognize that I've got 2 per AZ here because this is the simple build where I've got 1 public and 1 private subnet in each. And I won't go into NAT gateways and internet gateways and what the difference is, but essentially, again, I'm segregating my network here, in this case, by sort of security posture and by reachability to the internet. And then we want to put some instances in it, right? So a couple of VMs, this is what I actually want to do. I have to put these things in a subnet. They take an IP address from the range of that subnet, and I've put them in the private ones so that they're not directly accessible to the internet. So how similar is this abstraction that the AWS VPC is giving us to a traditional network? Well, it's not too far off. You can think of a VPC as a router, right? As a, I've gone and rented a router because I can make subnets and I can plug things into them. In the place of the few central firewalls that I showed before, we now have distributed firewalls essentially. So every subnet itself has a thing called a network ACL, which is pretty simple, only based on IP prefix, so I can stop one subnet talking to another just by IP ranges, and that's fairly old school. That's a kind of brute force thing, so that's the little firewalls I've shown here. But what we're really focusing on, what you're really meant to use is this idea of a firewall per instance, right? A security group, which lets me control communications in and out per instance, which is not something, unless you spent a lot of money on one of the newer things, Cisco ACI or something, was not something we could do in the old world. So this was, and AWS is what? VPC is getting on for 20 years old now, 15 years old maybe. This was a big leap back in the day, and this represented some, some real progress that we wanted about. We didn't just have to use and trust the firewall and the host or something, because that model was broken a long time ago. So now I've got these security groups and I've kind of got this distributed firewall. I can do access control per instance. So it looks kind of like a traditional network. Maybe the only big difference is that this is one layer 2 segment, right? This is one Ethernet domain. We used to call that a broadcast domain, but there's no broadcast in AWS. But everything, even across these subnets, is actually sort of layer 2 reachable from everywhere else. You would normally traditionally carve up VLANs, right? And each subnet would also live in its own VLAN, so they'd be layer 2 isolated. That's not actually the case in a VPC. How does it work? I mean, who knows, right? These are trade secrets. These are very complicated. Google's actually been fairly open with their stuff. As I say, they offer a slightly different piece of abstraction, but this paper on what they call Andromeda from Google is quite interesting. But the point is we don't really have to care too much, because these things offer a very good, very non-leaky abstraction. They offer us something that looks like a sort of traditional network, but with a few more smarts with this sort of distributed firewall and stuff, and it kind of just works. There are some edge cases. I once tried to get an IPsec endpoint set up in Google Cloud. I had to talk IPsec to something. So we were getting, it turns out we just didn't work, just couldn't make it work. And it turns out we were getting asymmetric routing because, of course we were, because IPsec. And the firewall abstraction, it's meant to look like an old centralized firewall device sitting at the edge, but it's not. It's actually distributed down into the software-defined networking layer. So the thing that was trying to decide whether to block my outgoing connections didn't have the state from the incoming connections, right? Because it looked like a central device. It was designed to look like that, but it actually wasn't. So there wasn't state in one place, and the connection tracking didn't work over this asymmetric routing. So there's these edge cases. Sometimes the abstraction comes up and bites you, but mostly it kind of just works. Right, and that's 10 minutes. I just wanted to get us all on the same page. We can start looking at the Kubernetes stuff. So yeah, a recap of AWS, VPC. Is that they're regional? People say to think of them as VLANs, and that's true. They're a flat layer 2 network, but they're not a broadcast domain really, because there's no broadcast. I prefer to think of them as a router with all the features that I can get from that. And as I say, I carve out one or more subnets per availability zone, and it'll go and route between them. So the Kubernetes cluster network. I think we'll start with Kubernetes publishes this thing called the Kubernetes Network Model. So I think it's easier to just, rather than try to do the big reveal by building it up, try to explain what we're trying to build. So the Kubernetes Network Model says an IP, the IP that a pod thinks it has, the IP that the pod sees on its interface, is the one it's addressed by externally. All of the pods can talk to each other without NAT, right? All of the pods can actually talk to the nodes as well, also without NAT. So this is all about it being a flat network. There's no jumping in and out through gateways. There's no little sub-networks. Everything is flat. Everything can talk to everything. And there's one address space that everybody agrees on. And also, we need when you're actually trying to build these things, there's a few little caveats, like every host process, so the kubelet, for example, which is what does the health checks, needs to be able to talk to any pod on its node. So however virtual and isolated you make your cluster network, the kubelet needs to be able to jump into it, get traffic into it. The interfaces tend to have layer 2 addresses. Pretend to be Ethernet interfaces and have MAC addresses. Whether or not layer 2 traffic works kind of depends on the implementation, and there's no bum traffic, right? So there's no broadcast, there's no unknown ether type, there's no multicast. It is a pretty straightforward, IP unicast network. So that's what we're trying to build. But how do we do it? So remember this, traditional network. Again, we're not too dissimilar to that, one flat space, one set of IPs, everything can talk to everything with a bit of security that we can add if we want. This, again, was deliberate. The Kubernetes folks have said this was deliberate to enable lift and shift. If you've got a daemon that runs on a VM, listens on an IP, you want to be able to move it into Kube and have it just about work. So logically, what does this Kubernetes network look like when we use it? I wanted to sort of pithily draw a blank page, right, to say there's no segmentation, there's no routing, there's no structure to it. What I haven't, the reason this pithy slide is here is I haven't added namespaces to this, right? I haven't added Kubernetes namespaces because they're not a security boundary. Folks are quite explicit that they are not a security boundary. They are one way that you can bulk identify pods. If you want to apply a network policy, or you want to identify objects in Kubernetes, you can put labels on them. Annotations aren't for that because annotations aren't indexed, but you can put labels on them, or you can often refer to them by namespace. But that's kind of a convenience thing. Namespaces were there to be, folders for accounting. They are not meant to be a security boundary, which is why I passive-aggressively haven't drawn them. But maybe a more helpful way of looking at it, right, is we've got 2 nodes, so 2 hosts, two VMs. I've put a couple of pods in each of them, and we want this blue thing. We want this one shared network between them, right? So wherever my pod is on any node, it can talk to any other node. We've got our flat IP space. No messing around. How do we build this? Well, Kubernetes doesn't care. You just have to end up with the properties that we talked about in the network model. There's very little prescribed way of doing it. So I'm going to go talk through one reference way of doing it, and then discuss how sometimes that's different. Okay, so let's start with one node. Okay, so this is one VM, maybe a physical machine, one Linux kernel. In fact, let's zoom in further to one pod. So what is a pod, right? First philosophical question of the morning. I think Liz Rice is here. She does this amazing talk on containers from scratch, which if anybody hasn't seen it, it's definitely worth a look through. She just literally live codes building containers. She live codes from Golang and actually builds containers by making the syscalls because there is no such thing as a container with a capital C in the Linux kernel, right? It's not a construct. It's this thing made from C groups and from this and from that and the other. And Liz live codes through setting all of that up. It's a really, really good talk. I'm going to skirt it a little bit here, but this pod is what we care about is these namespaces. So this is a Linux kernel feature. You may have heard of namespaces, process namespaces, PID namespace, the user namespace, the IPC namespace, mount namespaces. They are software, they're containers, right? They're software barriers. They're a software isolation mechanism for, the blue things are processes. So if I've got an Nginx process, a little supervisor D sitting alongside it, all of these namespaces stop these things accessing software resources, UIDs, PIDs and stuff outside of their namespace. I won't go into it too much, but essentially these things isolate these processes from the host, and they isolate these processes from processes running in any other container, any other namespace on the system. And a container basically uses all of them to isolate all of the different types of resources, but one of those is the network namespace, and that's the one that's going to be important to us. So this is a container. A container idiomatically would only have one process in, but you can have a little helper like this. So this one's got 2. So what is a pod? So a pod looks like this. A pod is one or more containers, glued together, but they share most of these namespaces. So pods run from images, right? So we need, a mount namespace is basically Chroot on steroids. So we need more than one mount namespace because we need to be able to Chroot into more than one, image that we've untarred. And they normally don't share PID namespaces for various reasons, but they do share the same set of users, or the time zone is the same in all of them, right? They can signal they can system 5 like IPC each other, they can signal each other. That's what the IPC namespace does. They agree on one set of UIDs and GIDs. It's really important for communicating with each other. So they basically share a security context, and they share a network namespace. So what is in a network namespace? Well, it isolates basically the whole network stack. So interfaces, right? If this is a pod, I've got this interface called ETH0. It's not the ETH0. It's not the interface that represents the physical NIC plugged into the box. Like more on that later. They've got their own loopback. So again, this will have address 127.0.0.1, but if one of these processes binds to it, it won't be able to talk to anything on the host. This is not the same loopback. It's another interface. It also isolates the root table, isolates sockets, Unix domain sockets and whatever, and it isolates iptables rules and netfilter config. So to cover the whole picture, right, of how this networking works and how things can talk to each other, how would two processes in the same pod, so maybe this one and this one, talk to each other? Well, you can think of a container as a little host, maybe, right, as a little isolated host. So that one of them can bind to loopback, and the other one can, just address 127.0.0.1, and they'll get there. This communication won't cross-talk with anything in another container, right, because this is a separate loopback interface. You could also bind to ETH0, and then somebody else could address ETH0, but that's also going to let people outside of the pod talk to you. So yeah, let's say like its little own host. That's not really an idiomatic way of doing things. There's a reason that I've, the thing in the sidecar here, this other container, I've put fluentd, I've put a log exporter, like what you would use secondary containers for, and the means that the way they would normally communicate would be a shared volume, right? So because volumes are mounted per pod, and you would normally, well, they're attached per pod, they're mounted into, because there's a separate mount namespace for each one, they're mounted into each container. But they would normally, containers in a pod, idiomatically talk to each other through a shared file system. But there's no reason they can't just, RPC each other over the local network. Okay, so starting to zoom out, how do two pods on the one node talk to each other? Well, they're kind of like two little hosts, remember? They've each got this Ethernet interface. So what do you do with two machines? You plug them into a switch. In this case, we've got a software switch, a virtual switch, so the Linux bridge device. And this physical analogy kind of continues a bit. So we need a patch cable, a virtual patch cable. Linux has got one of those. It's a thing called a VETH device, a virtual Ethernet device. It's actually two devices, the sort of two heads of each of these arrows. And when you make these devices, they come in pairs and they're connected together. So anything you put in one end comes out the other. So we can slave one of those devices, for each pair, we can slave one end into the bridge. And the other end, we can move into the network namespace. So if we create these things, out here, as it were, they're in what's called the root namespace. They're in the sort of default namespace of the host. I can take one of these devices at one end and I can move it into a namespace. And then it'll be called like VETH1234. I can then also rename it to, because you can rename interfaces, right? Everybody's machine blew up when the ENS0P3 thing happened, right? Nobody reads the release notes. So you can rename interfaces, and we can just rename that back to ETH0. That's honestly for backwards compatibility, right? But we can do that. But our pods are probably on different nodes. This is what Kubernetes is for, right? How do we get them talking to each other? So this is where our first interaction with the VPC comes in, right? So spoiler alert, we just bridge them into the VPC. We take the actual ETH0 on the host, we slave that into the bridge, and then we've essentially plugged two switches into one more switch, and we've just extended the network. It's not quite that simple in the way that I'm showing it. Most people don't do this, but I think this is a good way to explain it, and then I'll talk about the other options that are available. So zooming out again, what does our VPC see? We've got these two instances in the private subnets, but the VPC sees them as black boxes, right? It knows that it assigned an IP to each of them. It knows they've each got a singular IP, and they're in slightly different ranges here because they're in different subnets. But we know we've got multiple pods. We've got like a whole ecosystem. We've got a whole little network of little fake machines inside these things. So what do we do about that? Well, we can give those pods their own IP addresses. We have to give them in a separate namespace, right? In a separate range. The VPC won't let us reuse these addresses because it wants to do IPAM. So here I've chosen 172.16. So we can carve this range up between nodes. This node has obviously got 172.16.0. This one's got 172.16.1. Now I look at these slides. This should probably be 172.17, right? Because it's in a different AZ. But IPAM is hard. Get your spreadsheets out. But essentially, the point is you have to carve them up. So each of these nodes has a /8. And then how do we get these packets to flow? Well, we can just add routes, right, to these. So these are extra network subnets. We've used a private range. We're not going to interfere with anything. So we can just add routes to them. So any packet, leaving one of these pods, addressed to a pod on another node, it's going to hit this bridge. Find that the address isn't the bridge doesn't know anything about the address of the pod on the other side because it's not local, it's not plugged in. It's just going to be sent out the default route, which is down here. It's going to get dumped onto, looking back at this diagram, it's going to get dumped onto that VPC network at the bottom. And we need to arrange for it to get to the correct node. This VPC is flat and open, so it'll get there, but we need a route saying that actually 172.16.1 should be delivered to that other node and is in that other node. So that's pretty much it in the simple case, right? This is if you've done Kubernetes the hard way. I'm not trying to rip Kelsey off. If you've done Kubernetes the hard way, this is the way it talks you through building this stuff up, because I think it's a really nice way of showing how all these different things can plug together. But there are lots of different ways of doing this. Dumping packets onto the VPC. It may not be considered secure enough. They're not encrypted. They're going to mix with other VPC traffic. It may not scale well. AWS has got various limits around the size of the route tables. And so there's a bunch of other reasons, and there's a bunch of solutions, a lot of commercial solutions to them. The good thing is that this mechanism is pluggable. So there is a thing called the CNI, the Container Network Interface, and like it sounds, it's an API. So it is implemented by things called CNI plugins. A CNI plugin is a binary at the end of the day, a piece of code that's called when a pod is being made. So I would encourage you to watch Liz's talk, when all these namespaces are being built, when all the secrets are being built, one of the other things that Kubernetes does is goes and calls a CNI plugin and says, make an interface, get hold of a network interface for me that I will then move into the namespace of this pod and use in this pod. And they can go and do anything they want. So there's a built-in, plugin that comes with a system called Bridge, which makes a bridge and makes a veth pair and gives you the veth pair, plugs the veth in and gives you the veth. But there's lots of others too. And Kubernetes doesn't care. It just leaves it up to you to provide this plugin, and the plugin needs to do the right thing, otherwise nothing's going to work. A lot of those plugins will actually make an overlay network. Like I say, this setup just dumps packets into the VPC, and then you have to go reconfigure the VPC to make it do the right thing. A lot of them will actually make an overlay network by establishing tunnels between the nodes. So they use VXLAN, they use IPsec, they use WireGuard, they use MTLS, they use whatever they can find in the kernel, basically. Cilium is a very popular third-party CNI. It used to use IPsec for its tunnels. It now uses WireGuard. So then, of course, the VPC just sees this node-to-node traffic as standard. All the node-to-node traffic comes from one node and addresses the VPC address of the other node. So you don't need to reconfigure the VPC. You don't need to interact with it at all. As for the interfaces they make, they don't all necessarily make bridges. Some of them do. Some of them are like Calico, relies on routing. It actually doesn't make a Linux bridge. It alters the route table in the host. There's various ways that they do it. The interfaces that plug into the pods are not necessarily veths. They can be Mac VTAPs, or they can just be normal taps, or they can be, FDIO, VPP, access to crazy acceleration, all kinds of things. One thing they sometimes are, it's probably worth mentioning is, or certainly on the more modern AWS stuff, they might actually be in ENI. So we don't necessarily have all of this virtual networking at all. There's a CNI plugin for AWS that for every pod goes and makes a new ENI, attaches it to the node, and then every pod actually gets a VPC interface and a VPC address. So, in conclusion, this version at least is pretty much like yet another basic network. We've re-implemented that, and we've kind of said we want it to, because we want a flat network and we want lift and shift to work. So this maybe looks also like a traditional network. You know, it's just virtual interfaces and virtual switches and virtual cables. If you're wondering about the cool stuff, the IP tables and the BPF, well, there isn't any yet, right? This is all just routing and forwarding so far. We've kind of configured things. We haven't programmed anything. We haven't attached any actual hook code to anything. But so services. So at this point, we have a network. We have that overlay network where every pod can talk to every pod. And you know, this design does also satisfy the other elements in the contract, right, where pods can talk to nodes and kubelets can talk to pods and stuff. But in our traditional network, I won't spend any time justifying this to remove sysadmins, but we might want to run more than one instance of our service, right? That might be a good idea. So when a client, you know, on a traditional network, I've got a client over here, and it goes into a subnet, and it, you know, maybe goes through a firewall, and it's determined that that's okay, and you know, going from security context A to security context B is allowed or whatever. But anyway, the request gets in here, but we possibly don't call, you know, directly. We've got two instances of this thing. We're not going to call them directly. We're actually going to hit, you know, a load balancer, an F5 or whatever. And if you've built these kind of networks, you know these things have a management interface, and they also have a service interface, which holds several IPs, several virtual IPs. Depending on which service you want, you request a certain virtual IP, and you get forwarded to one of the backends. And these load balancers, they can get super expensive. They have features like, you know, TLS termination and health checks and protocol upgrade, and they can do all kinds of stuff. But think of the load balancer as something in the network. If you've ever plugged one of these together, it is a network device. It is not your network. It is a network device. You plug it in. You know, it appears in this virtual topology as a thing, but it's just something else that you plug into the network. It's not kind of part of the network fabric normally. So Kubernetes offers the same thing, right? Load balancing is totally something we want. You know, scale for resiliency, scale for load capacity. You know, horizontal scaling is what Kubernetes was basically designed for, and it's something we want a lot. So Kubernetes has this construct called a service, right? The service object on the API that lets us model a load balancer like this. And again, it's something in the network. So our logical view of, you know, the cluster network built by the CNI, it just works. It just moves packets around. We can make a service object which will give us one of these things that, you know, and you know, that logical diagram is really very simple. One thing to note is that for various reasons, you know, these service IPs do come from a different range, much like they would have done in a traditional network. You know, all the VIPs on your F5 would have come from a different range. So this is, I just fired Minikube up when I was writing this, and these are the ranges it uses. You know, obviously it's up to you, but you can see all the pods are in 10.244, and all the services are in 10.99 or 10.99.51 or whatever it is. It's actually quite difficult to introspect the ranges out of Kube through the API. Don't ask. So how is that built? Well, this load balancer from Kube doesn't offer any extra features, right? There's no vendor here trying to upsell you a bunch of stuff. This thing doesn't do TLS termination. It doesn't do HTTP protocol upgrade. It can't rewrite headers for you. All it does is that sort of, you know, layer 4 TCP UDP based sort of round robining. And more on those extra features later, because that's where the service mesh comes in. But this one is fairly simple. So it can just be some iptables rules. It doesn't need to be a network device. So I've got my kabam symbol here. This is my symbol for like iptables does something. So we attach iptables rules to E0, to the real E0, to the host E0, the path out of the host. So when a packet comes out of one of these pods, say one of these pods wants to address, you know, a service, it uses a service IP. So the packet comes out, it hits the bridge, which then says, well, that's not local, and it's never going to be because it's not a pod IP range, right? It's then going to send it out the default route, the default gateway towards off the host. This could be going to, you know, several places. It could be going to another pod IP. Fine, the VPC will take it to the right place. It could be going to an internet IP, you know, a public IP, in which case, fine, the VPC will take it out of its default gateway, and it'll end up, you know, on the internet. But if it's addressed to something in the service range, that's when these iptables rules kick in and get there before it leaves, and they rewrite the destination address to be one of the pods behind that service, right? So they do NAT, they do DNAT, destination NAT. They change the destination address, out to be one of the pods implementing the service. So then when it hits the VPC, it ends up on the right node and in the right pod. So that destination pod is then going to get a packet addressed to it. The destination address will be it. The source address will be the pod that it left from, because that hasn't been touched. So it will, accept it, process it, reply, and it'll send a pod back with its own address as the source address. The destination address is where it thought it came from, which was the other pod. So it'll get routed all the way back, and it'll end up coming in this ETH0 looking for the pod that it's addressed to, and that's fine. Like that destination address, the pod that it came from is good, but the source address on this thing is going to be the pod that actually handled it. But we thought that we talked to the service, and we're going to get very confused. We're just going to drop that thing as spurious if the source address on that reply packet doesn't match. So there's more rules in this blob of IP tables that do source NAT and change out the source address back from the service so it looked like the VIP replied. You can also do PAT, port address translations. You can also change out port numbers on the way. Sure, we've all written a Kubernetes service, right, that listens on port 80, and then the back end is like port 8080. That's just rewriting the port number. That's a convenience thing. So we're not multiplexing here. We're not brokering ports. That's just a convenience thing if you want to, if you want to add, wake up. If you want to add layers of abstraction, you can just add, I should have done that earlier. You can do port address translation as a convenience feature. So top turtle, and with 5 minutes to go. Right, so far we've got a network, traditional network, 2 layers of traditional network, well, built on God knows what under that, that kind of just work. And the first time we've had to get clever is when we want to do this load balancing, because we want to start using VIPs. So we've finally added some IP tables rules. Istio, I will not spend a lot of time explaining what Istio does. What would be the traditional equivalent? Imagine I can have, security next to every instance in all of my subnets, and this is a WAF, right? This is a layer 7 security device that can do cores, that can do HTTP access controls based on individual paths, all that kind of stuff. I don't have time really to explain what a service mesh is, other than to say there's not that many analogies probably in the traditional world. Again, ACI and VMX or whatever it was all promised to do this. Your mileage may vary. The logical view of it in the Kubernetes network is something like this. I've got my box, which is my pod, and every service now has a sidecar, now has a proxy alongside it. So in Istio's case, this is the Envoy proxy, and we want to send all traffic through the proxy because this thing is going to do resiliency, it's going to do observability, it's going to do security, it's going to do all these fancy things, and because it understands HTTP and MySQL and all these other layer 7 protocols, it can do them in a sophisticated, layer 7 kind of way. So this security boundary, this, subnet size essentially has come down to 1 because we know that this pod comprises of a network namespace, so nothing can go in and out of here unless it comes in the way we want it to go. So we've been shrinking our security boundary the whole size, right? We've now shrunk it to 1 essentially, and hence people then talk about zero trust, because when I'm in my own little world with the walls up, I trust nothing, or at least I implicitly trust nothing, right? Nothing is trusted by its network location. Nothing is trusted by the fact that its IP address has the same net mask as mine. The same prefix as mine, right? I trust it because I actually inspect the traffic and make a more sensible decision about what's going on. That was just my little rant to myself on all the FUD around the zero trust term. So what's actually happening? So our diagram is now looking like this. Within these network namespaces, we've got client and a foo service, and they've both got an Envoy. And remember, this thing is isolated. I've got a veth pair pretending to be 0. I've even got a little loopback interface. So both processes are within the pod's network namespace. They're separate containers, but that doesn't really matter to us. They're inside a pod. They're inside the same network namespace. When the client tries to send a request, it's probably actually going to be addressing a service address, but it's addressing something outside of this pod, so it's going to come out of this default route. So yeah, the client, but this isn't a network, right? This is more like a host. This thing. This isn't a network. There's no routing, forwarding in here. This is this thing, opening a socket on this interface and then calling connect and calling send using this interface. So there's no. This isn't a network device that can be a bump on the wire, is what I'm trying to say. This is not a network in here. This is more, I think of it more like a host. So again, the only way to get that traffic as it's leaving the client and heading down this VEF is IP tables. Something has to go and hook it and intercept it. So bang, more IP tables. We attach these rules to this fake ETH0, and they're going to pick it up and send it to Envoy. Actually, there's a bit of a dance. Envoy actually binds to low, and we intercept the traffic, and we send it to low, and then Envoy picks it off by listening from low, and then, but you know, the dance works, and we get to intercept that traffic. And this is the only way to do it. So this is more IP tables, and this I think is what a lot of folks get confused about. You know, you're throwing all of these rules and all these hooks around. You know, how do they compose? Why do they not interfere with each other? You know, does one system have to know about the other? The answer is no, and the reason is this isolation of these network namespaces is that I can put IP tables rules inside this network namespace, and they don't affect anything outside of it. I can put them here, and they don't affect anything inside any of these namespaces. So because these are different concerns, trying to do different things, you know, one is concerned with load balancing and getting me to the right, you know, a pod on a particular node, and one of them is concerned with intercepting traffic in and out of a pod. They sit in different places and they don't interfere with each other. But it is, you know, it's the same technology. Now, obviously, when I say IP tables, some of this stuff uses BPF these days because that's cool. But you know, net filter hooks. I'm just about out of time, so there's just a couple of little interesting things I probably don't need to really cover too much more. No, it just basically says the rest happens on the return path. The installation of these IP tables rules, like how they get here, it's a privileged operation to install hooks. I think you need capnet admin, or you need one of the capabilities around network. It's not something you want stuff running with all the time. So the thing that installs, I should have said, I guess, the thing that installs these rules is the kube-proxy component, right? So kube-proxy literally used to be a proxy. Kube-proxy used to be that box. It used to be a pod. I think they used HA-proxy or something, but it used to be a network device, right, that you plugged in, essentially. We now defer to the kernel. So kube-proxy, there's still a thing called kube-proxy, but it's basically a controller. It looks at the endpoint slice objects and all the other objects in the API server, and it reconciles it to these IP tables rules in the host. And there used to be an IP tables rule per service and pod. So all of the destinations, all of the pods on the back end used to be hard coded into those IP tables rules. That caused a huge amount of churn in all the IP tables rules when pods came and went. So now there's actually a rule per service that matches the service IP, and they defer to another kernel technology called an IP set, which is a set of IPs, right, that can be independently and much more quickly updated, so it avoids all of that churn. So kube-proxy is a controller that installs IP tables at the host. That has to run with some privileges, but it's essentially the control plane, right? It's part of the Kubernetes gubbins, like kubelets, you expect it to have some privileges. It's probably running in the systemd unit. You should manage it appropriately. Istio, though, also needs these things. So we don't really want the sidecar to run with those kind of privileges because it's a long-lived daemon. It's the thing that listens on the network. We don't really want that. So the traditional Istio way is to use an init container. That init container literally just has a bash. Last time I checked, just had a bash script that installed all the IP tables rules. So the init container runs with the appropriate capabilities, but it then runs to completion and goes away. Nothing at runtime then has the caps, and nothing at runtime can alter these rules, even if they get compromised. If you don't even like that, and some folks don't, those CNI plugins that I talked about, the things that are called to build the networking, build this interface ready for a pod, you can actually chain them, so you can have more than one plugin. So what you do is you take the plugin that actually makes the thing, Cilium or Calico or whatever, and you chain it with a thing called Istio init, which is like a fake CNI. It doesn't build any network interfaces, but because it runs with the kind of privileges you need, it installs these IP tables rules. So that's another way to work around this. So that's how they all get there, which I guess is what I wanted to say. And I'm probably done at that point. Thanks, everyone.